Part 2. Previously, we have already covered the fundamental and background of energy storage device. Now we come to part 2. We will now officially cover the knowledge of lithium-ion battery. So first of all, we will discuss why do we use lithium, and we will discuss the mechanism or the process of charging and discharging process of lithium-ion battery. And then we will talk about the thermodynamics, which is the cell potential of the lithium-ion battery. And we will talk about some other technologies beyond lithium-ion batteries. And finally, we will provide a list of terms for the definition of lithium-ion batteries. So why scientists are interested in using lithium? The motivation for using lithium metal as the anode of battery technology rely on the fact that lithium is the most electropositive material, which is minus 3.04 volts versus the standard hydrogen electrode. Electropositive means it is very easy to donate electrons and produce a positive ions. Lithium metal has a very low standard reduction potential as compared to the sodium, aluminium, zinc, etc. etc. And that's the reason why in the part 1, we mentioned that the battery that use lithium as the electrode will have a higher cell potential. That's because the anode have a very negative potential in the first place. However, lithium is relatively reactive metal and it has to be protected or it has to be free away from water and air. And that's the reason why we use non-aqueous electrolyte. This is where the polymer science come in and play a significant role in lithium-ion battery. Fact number 2, lithium is the lightest metal and hence the energy density of the battery will be very high because of the low molecular weight in the denominator. It can float on some oils in fact, so we have to use the oil that has a higher density so that lithium will sink at the bottom. The abundance of lithium on Earth crust is very limited and sometimes people will drift their interest to sodium-ion battery. As compared to lithium, sodium is chemically more active than lithium. However, the standard potential is less negative. Fact number 3, lithium ion has a very small ion radius and is easier to be transported under the influence of electric fields. Hence, lithium-ion battery has a better break capability as compared to sodium-ion battery or bivalent ions battery, for example, like calcium's or zinc-ion battery. The ionic radius of sodium-ion or calcium-ion is larger than the lithium-ion, and hence the rate capability, which is the kinetic of those ion, will be slower as compared to lithium-ion. The table here compare different metal in their physical properties, for example like atomic weight and density, electrochemical properties like redox couple, standard reduction potential, and capacity. The theoretical cell potential of a battery is the potential difference between the cathode and anode, without considering other factors like the stability of electrolyte or the compatibility of electrode and electrolyte, and the cost. An anode has a more negative standard reduction potential is generally better because the theoretical cell potential will be higher and lead to a higher energy density. Now let's take a look at the components of lithium-ion batteries. Lithium-ion batteries are composed of two electrodes, the anode and cathode, with an electrolyte in between of them. The electrolyte is an ionically conductive medium, which allows lithium ion to shuttle between the anode and cathode. The electrolyte allows the transport of lithium ion, but it does not allow the transport of electrons. The anode and cathode are separated by a separator. A separator is a non-conductive membrane which to prevent the direct contact of anode and cathode. Otherwise, it will cause thermal runaway. The separator has a porous structures which allow lithium ion to transport. The separator is made by polymer or ceramic, and we will cover more details in the battery component in part 3. Now let's take a look at the charging process and the discharging process of lithium-ion battery. First, we talk about the charging process. In the charging process, electrons are injected into graphite from the external circuit. So, to maintain the electron neutrality, lithium ions are intercalated into graphite from the solvent. Electrons are withdrawn from lithium cobalt oxide to external circuit at the same time, and the lithium ion migrate out from the lattice and dissolve in the ion. So this is how the entire electrical circuit is complete. In the external, we have electron flows, and in the internal, we have lithium ion flow. In the previous slide, we also mentioned that one of the advantages of lithium ion is the smaller ionic radius. In this case, we can see that the lithium ion can migrate, can intercalate or deintercalate from the electrode more easily as compared to sodium ion, which radius is bigger. And it also makes the structures more stable. So by combining the anode reaction and the cathode reaction, we have a full reaction of the charging process for lithium-ion battery. So in this charging process, the lithium-ion battery is converting electrical energy into chemical energy. In a discharging process, the whole reaction runs the reverse direction. The battery is releasing its chemical energy into electrical energy by doing work to the external circuit during discharge. And the electron will spontaneously move from a high chemical potential site to a low chemical potential site. The lithium ion migrate from the anode to the cathode through the electrolyte medium, and they are incorporated into lithium cobalt oxide through the following reaction and reduce cobalt from +4 to +3 oxidation state. Now, one interesting remark to make is that the cobalt electrode reaction is only reversible for X less than 0.5 and X is in a mole unit. So it limits the depth of discharge. Otherwise, the lithium cobalt oxide will be destabilized. The structures will crash or collapse very easily. So to maintain the structure's integrity or stability, the depth of discharge cannot more than 0.5 moles of lithium. Now, since we just talked about the charging and discharging process of lithium-ion battery, let's do a simple exercise to calculate the specific capacity of lithium-ion battery. Questions. Calculate the theoretical specific capacity of graphite and lithium cobalt oxide in lithium-ion battery. The molecular weight of lithium, carbon, oxygen, and cobalt are given as 7, 12, 16, and 59 grams per mole respectively. The Faraday constant is given as 96485 coulomb per mole. Now pause the video for several minutes before I go through this exercise with you. Okay, by doing some simple mathematical manipulation, you can get the formula of specific capacity is X times F divided by Nm. X is the number of electrons begin transfer, so when you multiply X with the Faraday constant, you can get the total charge involved. And Nm is basically the multiplication of molecular weight times the number of moles of the electroactive material. So in other words, N times M, you can get the mass of a material. By writing down the charging process or the charging process of the lithium-ion battery and plug in the number, we can get the specific capacity of graphite and the specific capacity of lithium cobalt oxide values, which is straightforward. In reality, those values could be lower because of some side reaction, for example, the formation of SEI, which we will cover later as well. So how does a commercial charger charge our phone? How does a commercial charger charge a battery in our phone? So the objective of charging our phone is to restore the battery to the full state of charge as efficiently as possible in a short period of time. Now we can either charge a lithium-ion battery by using constant voltage mode or by using constant current mode. Which one is the best? The answer is a combination of sequential, constant current and constant voltage. If you apply a constant voltage to charge the lithium-ion battery in the very beginning, the current could be too high and the raise of temperature could cause some side reaction. Taking a step back, let's say the lithium-ion battery is not overextended. However, the high C rate could cause a low capacity at the end of the day. And therefore, we should apply a constant current to charge the battery in the beginning to control the C rate of battery. And then the voltage will increase up to the theoretical cell voltage. So once the cell potential has reached the theoretical cell voltage, we say that the battery is fully charged. And therefore, the current will drop very fast because there's no lithium ion can be transported within the battery. If you do not apply any constant voltage afterwards and you let the battery stabilize after you charge the battery to the theoretical cell voltage, the voltage is likely to drop to a lower level after stabilize. So after you apply the CC mod, you need to apply the CV mod. You need to apply constant voltage to further top up the lithium-ion battery and also to prevent it from cell discharge. Because when you fully charge a battery, the battery will be in a very high energy state. It is unstable and it tends to cell discharge. Leaving the battery on a CV mode for long periods of time is called a flow charge. Now, if you charge a battery, you have a charging curve look like this. And when you discharge the battery, you have a discharging curve look like what is shown here. Normally, a flat discharge curve is desirable because it means that the voltage remains constant as the battery is discharging. So this flat region, or we say plateau, is called the nominal voltage, as we already mentioned in the part 1. And the high rate of discharge indicate that the voltage will drop very quickly and is only part of the capacity and energy can be used at a high discharge rate. We will talk about the potential drop in a lithium-ion battery. Other than the IR drop, there are other factors as well. So we will discuss this later. So what is the source of electrochemical drying force that allow batteries to operate? So what drives the battery? The answer is a gate-free energy. Gate-free energy is the maximum amount of work that may be performed by a thermodynamically closed system at a constant temperature and pressure. So the formula here is delta G equals to minus NFE. F is a constant known as a Faraday constant. N is the number of electrons involved in a stoichiometric reaction. E is a standard potential. If you are running the reaction in a standard condition, and we will put a 0 on top of G and on top of E. So if you are running lithium-ion battery, the N equals to 1 because we have Li plus. And if you are running magnesium-ion battery, N equals to 2 because we have Mg2 plus. The gate-free energy is determined by the entropy and the enthalpy of the electrode materials. The value of delta G can be calculated from the electrode material based on the chemistry that it involves. Here, E is the cell potential or the cell voltage. In a primary battery, we cannot change the gate-free energy. However, in a secondary battery, we can change the gate-free energy of a system by changing the cell potential. So if the delta G is a negative value, meaning to say that the battery can discharge spontaneously. There are a large number of possible material combinations which result in different cell potential. For example, like cathode, we have lithium manganese oxide, lithium cobalt oxide, and lithium iron phosphate, and lithium titanium oxide. And then for anode, we have metallic lithium, we have graphite, we have lithium silicate. So to make the electrode potential comparable, we use a reference, which is the metallic lithium. We define the potential to be 0, and you can see others material half cell potential as compared to lithium. As mentioned, the cell voltage of a lithium-ion battery basically is the potential difference between the cathode and anode, and this will give you 4.1 volts. And the actual voltage will be typically lower due to the IR loss. There is a cell voltage operating window in which you can safely operate the battery. You don't want the battery material to intercalate or deintercalate irreversibly, and often the stability of the electrolyte should be considered for a given cell voltage to avoid decomposition of the electrolyte. So one interesting phenomenon or one interesting observation is that the potential difference among anode is small. However, the potential difference among cathode is more significant and will play a significant role in determining the voltage of a battery. So the cell voltage of a battery actually will change when it's discharged. And we hope it can stay at a flat region, which is a plateau for a longer period of time. So a plateau potential is typically defined as a nominal potential. As mentioned previously, a battery cannot be fully discharged because it will destabilize the electrode structures, and therefore there always be a cut-off voltage to prevent the battery further discharge and to increase the lifetime of a battery. This is a very nice pictures of different electrode material. We have a positive material and we have a negative material. The positive material is the cathode and the negative material is the anode. So if you take the potential difference between the positive and negative electrode, you can get the theoretical cell voltage. If you look at the x-axis, which is a specific capacity, one interesting phenomenon is that you can see the metallic lithium has a highest capacity amongst other material. That's the reason why some people are still focusing on lithium metal as the anode. They are trying their best to solve the dendrite problem. Another interesting observation is that the specific capacity of anode is typically higher than cathode. We will discuss this in part 3. In the previous 3 slides, we talked about the theoretical cell voltage of lithium-ion battery. Now, we will contribute one slide to talk about the practical cell voltage of lithium-ion battery. If we discharge a battery at a high C rate, the capacity and the energy of a lithium-ion battery will be lost by heat. So what are the underlying factors contribute to this phenomenon? We need to study the polarization curve of lithium-ion battery at different overpotential. Here, the x-axis is increasing current or increasing overpotential, and the y-axis is a cell voltage. The IR drop is the potential of the cell drop due to the internal resistance of the battery. For example, when the current flow through the electrode material, for example like lithium cobalt oxide, there will be potential drop. When the current flow through the vinyl, is a polymer-based vinyl, there will be potential drop. And the IR drop can be minimized by adding more conductive agent, such as carbon black. However, this will sacrifice the gravimetrics and the volumetrics energy density. And we also have the activation polarization. So when a lithium ion transport across the interface between the electrode and electrolyte, it needs to overcome certain work function. So this will contribute to the activation polarization. Last but not least, we have concentration polarization. So this factor take into account of the resistance faced by the mass transfer, that is the diffusion process, by which the ions are transported across the electrolyte from one electrode to another. So this typically happens at high current density, especially when the concentration of the electrolyte, when the concentration of lithium ion in electrolyte is low. So the practical cell voltage of a battery will equals to the theoretical cell voltage minus all these potential drop. So when the battery age over time, this polarization or potential drop will also increase. So that's the reason why the practical cell voltage become smaller and smaller. Now we would like to talk about the cell technology beyond lithium-ion batteries. There are many cell technology beyond lithium-ion battery that has a higher energy density as compared to the conventional lithium-ion battery. However, these cell technology are not mature yet, and hence they are not commercialized and you cannot see them in the marketplace. Commercial lithium-ion battery has an excellent cyclic stability and reversibility. However, it has a limited capacity and energy density as compared to the advanced lithium-ion batteries. Lithium metal battery has a very high theoretical capacity and low redox potential. However, the formation of dendrite may cause thermal runaway and has a safety issues. And then we come to the dual ion battery. The dual ion battery, as the name suggests, that it has a dual ion. It's a two types of ion. One is a positive ion and the other is negative ion. And a dual ion battery has a high cell potential, which is 5.2 volts. And then we have high voltage lithium ion battery. Commercialized lithium-ion battery typically make use of lithium cobalt oxide. Now we can change. We can replace cobalt by nickel and manganese. As such, the cathode has a higher potential and the overall cell voltage of lithium-ion battery can be expanded further. Then we have a lithium oxygen battery, or we call lithium air battery. The cathode is in a gas form, which is oxygen. So the reaction happens at a ternary interface where we have a gas, liquid, and a solid. Last but not least, we have lithium sulfur battery. So the reason why we want to use oxygen and sulfur because they have a much positive potential as compared to the solid material. And one disadvantage of the lithium sulfur battery is that sulfur has a very poor electrical conductivity, and therefore we need to add a lot of conductive agents to improve the electrical conductivity. But this will sacrifice the energy density. We now come to the final part of the sharing in part 2. We will talk about some definitions of the lithium-ion battery. So this will help you to understand the technical specification of lithium-ion battery when you look at the manufacturer's brochures. Battery units. We have cell, modules, and pack. A cell is a smallest package from a battery that can take and is generally on the order of 1 to 6 volts. In lithium-ion battery, typically the nominal cell voltage is 3.7 volts. Modules. A module consists of several cells generally connected in either series or parallel. So if you connect the cell in a series, the cell voltage will add up linearly. The battery pack is the final battery that is installed in electric vehicles, for example. And a pack usually will consist of a protection system or a control system called BMS system. It's a battery management system. And some of the pack battery also has a cooling system. To give you an example, we can use 12 cells to construct a module and then to use 8 modules to construct a battery pack. And inside the battery pack, we can have some cooling system or BMS system. Now, let's move to the battery condition. State of charge is defined as the present battery capacity as a percentage of maximum capacity. And the depth of discharge is basically 1 minus the state of charge, SOC. Typically, a battery is discharged to about 80% of the original state of charge. Further discharge of a battery will cause the structures destabilize. And then we have terminal voltage. The terminal voltage is defined the voltage between the battery terminals with load applied. And then we have an open circuit voltage, which is the voltage between the battery terminals with no load applied. So if there's no load applied, there will not be IR drops. So that's the difference between the terminal voltage and open circuit voltage. So you can use a multimeter to measure the battery terminals and you can get the open circuit voltage. And then we have a nominal voltage, which is usually a voltage given by the manufacturer. The actual voltage will be around nominal voltage because when we discharge the battery, the cell voltage will decrease. So the nominal voltage is usually around the plateau, the flat region of the discharge curve. The cutoff voltage is the minimum allowable voltage. So usually we will not fully discharge a battery. When it's discharged up to 80%, or we say the state of charge is 20%, we will cut off the battery. Otherwise, the structure of the material will be destabilized. The capacity of a battery, which we already discussed already, and we say that the capacity is C rate determined. And then we have cycle life. Cycle life is the number of discharge and charge cycle that a battery can experience before it fails to meet certain performance criteria. Now, let's come to the summary of this section. We mentioned that why people want to use lithium to develop lithium-related battery. Lithium has a very low reduction potential and it has a low molecular weight, which gives rise to high energy density, and it has a small ionic radius. And then we also cover the concept of charging and discharging process for the lithium-ion battery, how the lithium ion can shatter, intercalate or deintercalate from an electrode material. We also cover the concept of cell voltage from a perspective of thermodynamic heat-free energy. We also talk about the theoretical cell voltage and practical cell voltage. We go through the concept of cell technology beyond lithium-ion battery. And last but not least, we cover some definition of the terms that commonly seen in the lithium-ion battery. So that's it for this chapter.